The previous video talked all about that electromagnetic spectrum and how there's all these different kinds of um, radiations that differ on their wavelength and their frequency. But the really amazing part is that they all travel at the speed of light. They all have one thing in common. So that speed of light is a constant, which is the lowercase c, capital C is for carbon, and this is 3.00 times 10 to the 8th meters per second in velocity. That means 300 million meters in 1 second's time, the time it takes for you to clap. Yeah, I heard you clap. All right, so 300 million of those meter sticks. It's an unbelievable distance. But what you notice with these is that if you had a short wavelength, you had a large frequency. And if you had a long wavelength, you had a small frequency. So what is the relationship? C is equal to lambda times F, where lambda is your wavelength. Okay, this is an inverse relationship. When one goes up, the other goes down. When one goes down, the other goes up. Because these two numbers multiplied by one another is a constant. And that's where we get this 3 times 10 to the 8th meters per second. So one of the things that you'll see on here, frequency is either given this Greek letter nu, or you can use the F, okay, for frequency. So teeny tiny little cosmic waves where you see a high frequency is going to have the smallest wavelength, and where you are going to have the lowest frequency and not see them so often is where you are going to see the longest or biggest wavelengths. So those radio waves, they're all going to be really, really long, and then they're going to get more and more frequent here on this side. And then we see in that very specific range here for visible light. Remember again, this is micro meters for a very, very small amount in there. All right, so let's take a look at a sample problem. Okay, it says, what is the wavelength of a yellow light emitted by a sodium lamp? Okay, and yes, that's why street lamps are little yellows, because they use sodium inside their filaments. It has a frequency of radiation of 5 times 10 to the 14th reciprocal seconds. So what is given to us? We are given that the frequency is equal to 5.10 times 10 to the 14th reciprocal seconds. We are looking for the wavelength, and the parent equation that I use to solve between the two is going to be C equals F times lambda. So I need this constant C. So it'll be given to you on your papers. You do not need to memorize it, but we use it so much that you kind of commit it to memory. You are looking for what our wavelength is going to be. So how do we solve for wavelength? All right, believe it or not, C equals F wavelength looks very, very tricky because it has all of these different variables in it, and some of them are Greek, but it's really no different than solving 6 equals 2x. So what does x equal here? Well, what we're doing is we are dividing both sides by 2, and we get x to equal 3. So if we want to know what lambda is here, we're going to divide both sides by f, and we get lambda to equal C over F. So this is the rewritten version that we're going to plug into. Lambda is equal to C over F. And then let's plug in what we know. Okay, so 3.0 times 10 to the 8th meters per second is our speed of light. And then we're going to plug in 5.10 times 10 to the 14th reciprocal seconds. So how do I solve for this in my calculator? In my calculator, for anytime we have a times 10 to the, remember we use the E button. So 3.00 E8 divided by 5.10 E14. So please go get your calculators and come back and make sure that you know how to plug those in. Per seconds and reciprocal seconds will cancel out. Our wavelengths will be in meters, and you should get 5.88 times 10 to the negative 7th meters. All right, so since this is going to be something that we can see, in light that we can see, we can change that into nanometers. 5.88 times 10 to the negative 7th meters. We know that 1 times 10 to the negative 9th meters is a nanometer. So this is the same as 588 nanometers. So you'll see on our next slide, it's all typed out for you. Feel free to push pause if you need to see it a little bit closer. But since we are given frequency and we have our constant and looking for our wavelengths, we are going to solve, okay, by dividing both sides by our frequency. And then you see that frequency and frequency cancel out, leaving this. You're never going to solve for C, all right, because that's a constant. And then you plug everything in, and you get your 5.88 times 10 to the negative 7th meters, which is 588 nanometers. All right, with that in mind, frequency also has with it a certain amount of energy. All right, I showed you those waves that we had, okay? And here we have the really, 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 really tiny wavelengths over here. Imagine you were on a little boat, okay? This boat right here, you might be happy and good. But if you're on this boat going up and down over here, you're going to feel quite bad. Why? Because there's more energy here with more frequency. And here where there is low frequent waves, that's going to lull you to sleep. So there is low energy and you're going to be super happy. Different colors have different energies as well. So that was all determined by Max Planck, who also was around the same time as all of our famous Einstein, Schrodinger, and all them. So in the early 1900s, also found that direct relationship between our frequency and our energy. And E equals HF is the equation that he used. So the energy of a photon is equal to a constant, a proportional amount, times the frequency. Okay, so this unit that you see here, joules times seconds, Joules, is a unit of energy in the scientific community. Here in the United States, we use calories. You might say kJs as well on some food packaging in other countries, and we'll get into that in chapter 11. Is going to be your kilojoules. So it is basically taking into account how many joules of energy you see per frequency of the wavelengths that come by. So if we're using this, we can solve what the energy of a photon is with a frequency of 5 times 10 to the 14th reciprocal seconds. So we are given a frequency of 5.0 times 10 to the 14th reciprocal seconds. We are looking for the energy, and the parent equation we're going to use is E equals, HF. So H is a constant that is available to us as well. 6.63 times 10 to the negative 34th joule seconds. No, you don't have to memorize it. And then we're going to plug everything in. E is equal to 6.63 times 10 to the negative 34th joule seconds. and we're going to multiply that by 5.0 times 10 to the 14th reciprocal seconds. When those two things multiply by one another, seconds and per seconds are going to cancel out, leaving the energy in just joules. So to remind you, when I put this in the calculator, we have to use the EE button because we're using a number in scientific notation. This keeps our order of operations okay. So get your calculator. Hey, you're back. All right, 6.63 E negative 34 times 5.0 E14, and you hit enter. So that's what should come up in your calculator screen, and you should get a value of 3.32 times 10 to the negative 19th joules. Okay, and that is the energy of that photon. So, like the other slides, here it is all typed out for you in case you can't read my chicken scratch. I'm sorry, everyone. But we are given the frequency here of 5 times 10 to the 14th. Our constant is 6.63 times 10 to the negative 34th. And we are plugging into E equals HF. And then we plug in, seconds and per seconds cancel out, leaving the joules behind. And this is how much energy one photon would be. So then you can use this as any other calculation to maybe figure out how many moles. And then from there, maybe you can figure out how many grams. But that'll be in additional chapters. All right, everybody, that is frequency, light, wavelength, and energy.